was saying it's an honor to introduce John Hopcroft from Cornell University. He is the IBM Professor of Applied Mathematics and Engineering. John has been on the forefront of computer science research since 1964, his graduation from Stanford University. So this is a very long time. His research accomplishments are legendary. Let me remind you of a few of them. There's a seminal book on automata theory and formal languages. There's a textbook on algorithms and concrete complexity. He's well known for his famous algorithm with Tarjan on graph planarity and on BitPipe on bipartite matching. Fast algorithms for graph isomorphism and the analysis of permutation groups is another one of his accomplishments. He has worked in robotics and geometric modeling. He has spearheaded electronic prototyping. And more recently, he has done the social networking analysis of huge graphs, including things like analyzing the role of gossip, PageRank analysis, and so on. Now, coincidentally, the list of rewards and recognition that he has accumulated over the years is equally impressive, if not more so. He's a member of the National Academy of Sciences, member of the National Academy of Engineering. He's a fellow of the American Association of the Advancement of Arts and Sciences. He's a fellow of the IEEE, fellow of ACM, fellow of the American Academy of Arts and Sciences. In 1986, he received the Turing Award. In 2005, the IEEE Gooding Memorial Award. The ACM Karlstrom Outstanding Education Award came in 2008. In 2010, he was awarded the German von Neumann Medal. He served on the Science Advisory Board for President Bush and Clinton from 92 to 98. This was Bush 41. He's on the advisory board of the Packard Foundation and of the Microsoft Technical Advisory Board. He's even the Einstein Professor of the Academy of Sciences in China. So it doesn't get much better than that. So today he will talk to us about new trends in computer science. And from his unique perspective of 50 years of being at the forefront of computer science, we can expect some fantastic insight into what's coming and what's going to evolve in the field over the next 50 years. So let's give a warm welcome to John.
Thanks very much, Chris. And it's a great pleasure to be here and have this opportunity to talk to you about the future of computer science. And what I'd like to do is I'd like to just tell you a very quick story about my career. Because I graduated from Stanford in 1964 from an electrical engineering department. There were no computer science departments. I was hired at Princeton in an electrical engineering department. But fortunate for me, the chairman of that department could see the future and asked me to develop a computer science course. This was one of the first computer science courses taught in the US. And what it did for me is it made me one of the country's first computer scientists, and therefore whenever they were looking for a senior computer scientist, I was on the short list. And so I got opportunities to serve on the National Science Board and things like that, which if I had been in high energy particle physics, I would still be waiting today for the senior faculty ahead of me to retire to have those kinds of opportunities. And students often say, well, you were just lucky about the time you graduated. And part of the message I want to leave with you today is you're every bit as lucky because there's a fundamental change in computer science taking place. And if you position yourself for the future, you will have a fantastic career. In the early years of computer science, we were interested in making computers useful. So we were interested in programming languages, compilers, operating systems, and things like that. In the future years, we're going to start looking at what these computers are used for. And we're going to do things like track the flow of ideas in scientific literature, track the evolution of communities and social networks, and so forth. I'm going to move through these slides pretty fast because all I want to do is just give you kind of a vision of the future, and then I will talk about the science that's going to be needed to support that future. So the drivers of this change, some of them are the merging of computing and communications, the wealth of data available in digital form, and the fact that there are devices and sensors everywhere. And the implications for at least theoretical computer science is we need to develop the theory to support these new directions, and we need to update computer science education. Okay. So what I'm going to do is I'm going to divide my talk into 3 parts. The first part I'll go through rather quickly. It's kind of just a show and tell to give you a glimpse of what the future might be like. Then I'll talk about the science base needed to support these activities. And finally, everybody tends to ask me, what do you mean by a science base? So I'll show you an example of one. One of the things you're going to be faced with is enormous amounts of data. I guess the only thing on this slide is that every day we broadcast approximately 174 newspapers per day for everybody in the world. And might ask you, have you read your 174 newspapers today? That's the amount of data that you're going to be dealing with. If you look on the web, there's over 20 billion web pages. If you look at something like Facebook, there are 485 million active users in a month. And I'll just point out one thing. In one day, per day, people upload 250 million photos. So if you think about that for a year, the amount of photos out there. And what are we going to do with some of these photos? There are people in computer science who are looking at various photos, and they're constructing 3-dimensional models from these photos so that you can walk around and tour and see exactly what these historical things are. Another thing, there are security cameras. If there's a criminal event somewhere, people probably can identify the person from a security camera. It's probably going to be recorded. If you want to know who somebody is, you might type in a search request to Google. Maybe if I put in a search, I would want to know if I've ever met this person. And sure enough, they would, by face recognition, determine it was in this lecture that I taught and tell me a little bit about the person. Physicists talk about how they found a basic elementary particle. What they don't point out is it was computer science that actually found it for them. What they did is they generated 1,000 trillion proton-proton collisions. They obviously, no human being looked at those. That was a sophisticated computer science program that actually found that particle. And one of the basic things is that the current database tools are just insufficient to capture, analyze, search, visualize the size of data that we encounter today. And what I wanted to do is just give you a glimpse. It's almost every domain, whether it's economics, whether it's sociology, whether it's biology, they're running into big data, and it's computer science tools that are solving their problems for them. And so what we need is we need a theory to support many of these activities. Things like large graphs, spectral analysis, high-dimensional data. And one thing up here, you might wonder about this bottom one, sparse vectors. So I'm going to just pick that one to tell you a little bit about sparse vectors. We need a theory of sparse vectors, and a sparse vector is a vector, a high-dimensional vector, almost all of whose components are 0. And why are these interesting? Well, they come up in many areas of science. They come up in tracking the flow of ideas in scientific literature, in biological applications, signal processing. And I'll give you one application. I'll just talk about a biological application for a minute. Suppose you had an orchard and you were growing apple trees, and what you wanted to do is you wanted to get better apples. So what you might do is you might have a matrix where the rows of this matrix, there's one row for each tree in your orchard, and the columns correspond to positions on the genome for the apple. This vector here is an unknown vector. You want to know what genes give rise to certain observable phenomena. Maybe like you want nice big red colored apples or something like that. And so what you want to do is you want to solve this linear system of equations. And the first thing you're going to tell me is that's ridiculous because there's many more columns than rows, and there's a whole vector space of solutions. How can you possibly solve it? But it turns out if you ask for a sparse solution, it'll be unique. And there are two reasons for that. One of them is biological, and that is that if there were two sparse solutions, that would say there were two sets of genes which gave rise to this particular property. And evolution is very thrifty. It just doesn't evolve two sets of genes to do one thing. So physically, it better be that there's only one sparse solution. And then the other reason is there's some mathematical reasons about that matrix that says there'll be only one sparse solution. And if you want to try, you can do an experiment. Just build yourself a matrix and generate the elements in there at random, say from a normal Gaussian. Pick a sparse vector, multiply it times the matrix and get your observable vector. Then go back and ask, is there another solution which would give you the same observables, and you'll find out there is not. And understanding mathematically why that's true is going to be something important. So on that previous list, there are a bunch of areas of mathematics that we're going to have to understand a little bit better. So I'm going to talk about some of the things you're going to do. One of them is you're going to digitize medical records so that I can go anywhere in the world, and if I become ill, I can go in and see a doctor. He can download my entire medical history, figure out and give me the best possible medical advice. Okay. However, I don't want my insurance company to know everything about me. And in fact, I guess I should have changed this slide. Really, all I want the insurance company to know is that they have to pay a given doctor a certain amount of money. There's no need for them to know who the patient was or what the conditions of the patient or anything of that type, right? All they need is a rigorous proof that they have to pay a certain amount of money. And similarly, you want researchers to have access to this database, but you don't want them to get any individual information. You only want them to have statistical information. So how are we going to do this? Well, there are some ideas like zero-knowledge proof and differential privacy. I'll tell you about a zero-knowledge proof. A zero-knowledge proof of a statement is a proof that the statement is true without providing you any other information. And that's exactly what I want to give to the insurance company. I want to give them a proof they have to pay Dr. So-and-so a certain amount of money, but they don't need to know why or anything else. Okay, so I'll give you an example of a zero-knowledge proof. I'm going to take a simple example. This is a Sudoku game. I'm assuming everybody knows how to play Sudoku. You want to fill in the missing numbers so that every row, column, and 3x3 square has each integer between 1 and 9. Okay. Well, what I would like to do is convince you I have a solution to this without giving you any information about the solution. So what I'm going to do is I'm going to take some little pieces of cardboard, and I'm going to write the numbers down for the solution. And then I'm going to put the cardboard face down so you can't see the numbers on the particular squares. And then I'm going to claim I have a complete solution. Now, you probably don't trust me, so you're going to say, I want to make sure you have a solution. So I say, pick any row, any column, or any 3x3 square, and I will pick up the pieces of cardboard, I'll shuffle them and hand them to you, and you can check and see that there's numbers 1 to 9. Okay. If I cheated, there's a probability of what? 1 over 27, you're going to catch me. Okay? But if not, and then what I'm going to do is I'm going to take the pieces of cardboard and put them back down. Now what you can do, but you don't get to see where I put them back down. Now what you're going to do is you're going to say, I want a little bit better proof than that. Show me another row or another column. And after you've gone through a fair number of these, you're going to be convinced that, yes, I have a solution. But you're not going to know anything about the solution because you don't know where the numbers go. Now, one thing you should realize is that I may not put the numbers back on the same squares they were on when I picked them up. So it's not a proof in quite the same form as an absolute proof. It's just I can force the probability that I've cheated, you can force it to go to 0 by asking me a few million times. Okay, so I'm going to give you a slightly more complicated one. There is a problem called graph 3 colorability. And what you want to do is you want to color the vertices of the graph with 3 colors so that the opposite ends of each edge are different colored. And this problem is a problem which is NP hard, and so for a large graph, we don't know any polynomial time algorithm for it. So I'll show you a zero-knowledge proof that I have a coloring of a graph. So it may be a situation, I'm running a business where I do 3 colorings of graphs. You have a graph with 1 million vertices, and you want to know if it can be colored with 3 colors. But we can't do business for the following reason. We don't trust one another. I'm afraid if I show you the coloring before you give me the money, you may say, oh, I'm not interested. And you don't trust me that if you give me the money, I may not have the coloring, and then you lose your money. So what I need to do is I need to prove to you I know how to color this graph without giving you any information whatsoever all about how to color it. Okay. So what I'm going to do is I'm going to create an envelope for every vertex in the graph. And I'm going to take a colored piece of paper of the color that I'm going to color that vertex. I'm going to stick it in the envelope and seal it. And then I'm going to tell you, just as I did for the Sudoku game, pick any edge you want, and I'll give you the 2 envelopes and you can open them. Okay? So you open them, you see they're different colors, and you say, well, you got that edge right, but there's 3 million more edges. I'd like to see some more edges. If I let you see another edge, then I've given you some information. So I can't do that. So what I do instead is I take all the envelopes and burn them. I permute my coloring. If I have a coloring, I can permute the 3 colors. I'll seal the envelopes up again and go through. And you can ask me for a few million edges, and pretty soon you'll be convinced that I have a coloring. Okay, now one of the things you might say, that's an awful lot of paper, and it's going to take a lot of time and so forth. But what we're really going to do is we're going to agree on an encryption system whereby I encrypt the colors. And there's some subtleties about that you have to worry about. But it's only going to take 1/millionth of a second to do one of these tests. And so you can ask me about 1 billion edges and be convinced that I've got a coloring. So it's not just in the digitization of medical records that this is going to come up, but it's going to come up in almost every database you create. I'm going to talk about GPS, but supply chains, transportation systems. I quite often drive to Philadelphia, and one of the things I do is I take a road, this yellow road from the top, and I want to get on this Interstate Highway 81. And the guidance system in my car always routes me like that. But I notice when I go that people seem to be turning off much earlier and taking this another road. And so I started taking that. It was a little better. And then I saw there was even another way. And the question is, why did my route guidance system not give me the optimal solution? And the reason is they don't know the condition of these roads, and so they will only keep me on state highways. They won't let me go on side roads. However, suppose that everybody in their car recorded their GPS coordinates, and when they went in for service, they downloaded them. Then with a little computer program, we could see what local people did, and we could find this optimal savings. Now, you may not think that this is very big, but if this reduced the mileage by 1%, we would be talking about tens of billions of dollars. Okay? So these are important things that you're going to do, and you're going to be squeezing out that last 1% in many things. But why don't we do this? Well, if I let you have my GPS coordinates, you will quickly find out who I am by where I park my car at night. You'll find out where I work, you'll find out where I shop, you'll find out everything about me, which I may not want to let you know about. So what you're going to need is you're going to need a way of downloading these GPS coordinates without giving any information away about who generated, where, why, and so forth. Okay, so I'm just trying to give you a sample of some of the things that you're going to do. In the past, sociologists could just study groups of individuals of a few thousand individuals. But today, they can study hundreds of millions of individuals and their interactions. And one of the important activities is to just understand how communities form and evolve. And so I'll talk a little bit about some of the work there. The early work took graphs and divided them into subcomponents, and then divided these subcomponents on down. And some of the things that they did is they defined a community to be something with more internal edges than external. But that's not true. Most people have more, I'll show you a slide, have more external than internal to a community. And so there are a number of problems with some of the early work as really being applicable. And by the way, I'm going through the slides very quickly. If anyone wants them, I think Chris can make them available to you. Okay. So this is a community. That red or black dot is me. This yellow is theoretical computer science. And I have a number of connections in there, but I have many more connections outside that community to family and friends, to classmates, to colleagues at Cornell. And it turns out I'm in many communities. So even asking the question, what community is a person in, probably doesn't make sense. What you're going to do is you're going to pick 3 or 4 people and say, what community do these 3 or 4 people define? Okay, so I'm going to talk a little bit about this, ongoing research on finding communities. I'm going to first explain something called spectral clustering and how that works. And so I have a very simple example of a matrix of a graph where there are 3 communities, that's these blocks of 1s, and the communities are very strong because everybody in the community is connected to everybody else, and there's absolutely 0 connections outside. This is just to illustrate things. So the way spectral clustering works is it finds the first 3 eigenvectors, or singular vectors, and that's what this matrix, they make a matrix over here. And then what they do is they take each row of this matrix and map it into a 3-dimensional space. And so all of the rows of that first cluster went to that first dot, the next cluster, the next dot, and the next cluster. And if it turned out I hadn't made the community absolutely completely connected, if it was made up, you had a fair number of connections within the community, but not all, and you'd had some connections between communities, what would have happened is those 3 points where everybody got mapped to would actually spread out into kind of a cluster. And then if you used just a clustering, k-means clustering, you would get the clusters that corresponded to the various communities. Now there's a problem with this, because this assumes that you're going to be looking at the global structure of the graph. And the graph has maybe 100 million vertices, and you're going to end up with communities of size 30 million or something. That's not what you really want. You want to find communities of size about 50 in here. So how can we modify this technique to make it work? Well, one of the first things I should point out is, what if the communities overlapped? Because my example, they didn't overlap. And if they overlap, here you would expect to get 2 clusters. But since they overlap, what you really are going to get is you're going to get 3 clusters. And in fact, if you had n communities, you'd get 2 to the n clusters, so there's a problem. So what you should do instead is, instead of clustering the rows of the singular vectors, what you want to do is find the minimum 0 norm vector in the space spanned by the singular vectors. Okay? And actually, you don't want to find the minimum 0 norm vector, because that would just be 0. So what you want to do is you want to require that at least one component should be 1. And what this says is, you take, let's say there are 3 people and I want to find the community they're in. I will set the components corresponding to those 3 people to 1. So when I find the minimum 0 norm vector, what I will get is I will get the community defined by those 3 people. Now, finding the minimum 0 norm vector is NP hard. So what I'm going to do is I'm going to switch to the minimum 1 norm vector and just use that as a proxy. And this turns out this is just a linear programming problem, so you can solve it very, very quickly. But what I described is a method which is going to find the global structure of the graph. And what I really would like to do is find the local structure. So how can we modify this technique? And I'm going to give you a physical example to illustrate what I'm going to do, and then I'll show you how it actually would work here. Suppose I had 3 pools of water, and they're connected by narrow isthmus. And I drop some dye into one of the pools. If you look at that dye just after I drop it, you'll know exactly where I dropped it. But if you wait a little while, you'll know what pool I put it in, but you won't know exactly where. And a little later, you'll still know the pool, but it'll start to spread out to the others. And when you wait, it'll be completely spread out. Okay. When you find the singular vectors, you're dealing with this structure here. But what we would like to do is why don't we go back and deal with this structure? Because this will find for me the local community. So what I'm going to do is the following. The way you would get the singular vectors, one way to get them, is you do a random walk and you walk long enough until the walk converges to the stationary probability. Instead of doing that, I'm going to take a very short walk. I'm only going to take 4 or 5 steps. And when I say I'm taking a walk, what I'm really doing is I'm pushing the probability out. I'm not actually doing an individual walk. So what I'm going to do is I'm going to take my probability vector x, which maybe will have 3 1s in it and the rest all zeros. Those 3 1s will indicate the people whose community I'm trying to find. I'll take 1 step, 2 steps, and I'll take this dimension, this vector space of size 3, and then I will move that through some number of steps. That's why I multiply it by a to the 5th. And then what I will do is in the space that I've generated, I'll find the minimum 1 norm vector. And what that will do is that will pull out that local community. Okay. Now it turns out the minimum 1 norm vector is not going to be an indicator vector. An indicator vector, it would be 1s for everybody in the community and 0s for people outside. So with real data, what I'm going to have to do is I'm going to have to threshold that and cut it somewhere. So what you will get is you'll get a vector that looks like this, and you'll have to decide where your community ends. And that's a problem we don't have a good answer to right now. Okay. And actually, you're not going to really want to find a vector in the subspace, but you're going to want to find the minimum 1 norm vector, which is close to the subspace. So what I'm going to do is I'm going to minimize the 1 norm. I'm going to find y to minimize the 1 norm of y plus some constant times the angle with respect to the subspace. And this is just a quadratic problem that you can easily solve. And you can decide how you're going to balance how close you want it to be to the subspace versus how minimum 1 norm is going to be. Okay. And so some interesting problems that are going to come up there is how long should the random walk be, what dimensional subspace should I push through, and things like that. Questions you might like to answer is how many communities is a given person in? What are their sizes? How many seed points are needed to uniquely specify a community? And which seeds are good? It would be nice if I picked somebody who is sort of interior of the community, not somebody who is just roughly on the boundary or barely in the community. So these are questions. And I'm going to skip just for theory. What I hoped I've done at this point is suggested that there are a large number of mathematical problems where we are going to have to develop a science base which is going to tell us how to solve them. And so I thought what I'd do in the next section of the talk is I'm just going to talk about a few areas like a theory of large graphs. I mean, when I went to school and studied graph theory, graphs had 10 or 15 vertices. You could draw them on a piece of paper. Adding an edge or removing an edge would probably change a fundamental property of the graph. The graph theory that you're going to need to develop is one where your graphs have billions of vertices. The exact edges present are not critical. If I randomly erase 1% of the edges, I'm not going to change any interesting property of the graph. You've got to be able to prove some basic theorems on it. So that's what we need. Now, the first version of a theory, due to Erdos and Rainey, they developed this model where you put down your n vertices, and then for every edge you flip a coin, which comes down heads with probability p. If it comes down heads, you put the edge in. If it doesn't, you leave it out. Okay. Now, what that does is that gives you a graph. You can prove a lot of theorems about it. And one of them is if you look at the vertex degree, it'll be a binomial degree distribution. Now, the difficulty is somebody went out and looked at a real-world graph. And if you look at it, say, United Airlines route map, you'll notice that the degree distribution is anything but binomial. There are some cities like Chicago and Los Angeles, San Francisco, very high degree, and there's a large number of cities which is just degree 2 or 3. So then what people did is they changed the model to a generative model. And what they did is they just put down a few vertices and edges at the beginning, and then at each unit of time they added some additional vertices and some additional edges, and they just needed a rule to determine where to place the edges. And if they used the rule of preferential attachment, where the probability you select a vertex to attach the edge to depends on its degree, the higher the degree, the higher the probability, then you will get a power law degree distribution, which is what most graphs in the real world happen to look like. So get something like that. Another example, I went to and when I teach a course, I always ask students to go out and find a database that they can easily convert to a graph. And then find the number of connected components and their sizes. So I took a database I found in Science. There were 2,730 proteins. Each protein is a vertex in my graph. There were 3,602 interactions between proteins. Those were edges in the graph. When I found the connected components, I found 48 components which of just isolated proteins, 179 of 2 proteins which interacted with themselves, and so on. And I went out here. There were 16 proteins which interacted. But when you do something with real data or write a computer program, you always ought to check your answer, right? So what I did is I took the number of each size component times the number of vertices in that component, multiplied them and added them up, and I got 899 proteins. Where are the other 1,851 proteins? Make an error in my computer program? Well, what I did is I decided, well, I'll run it a little further and see if there isn't something bigger. And sure enough, there was a giant component with 1,851 proteins in it. Okay? Now, it turns out you can pick literally any database you want, and it'll have this kind of structure. There'll be a giant component. So it's probably pretty important to understand why giant components form and understand them. Something else you're going to be dealing with is you're going to be dealing with high-dimensional data. So it would be good to understand high dimensions. And one of the things is my intuition was formed in 2 and 3 dimensions, and it turns out it was totally wrong for high dimensions. Just to give you an example, if you put down a number of points at random in 2 dimensions, and you calculate the distance between the 2 closest points and the 2 farthest apart, there'll be a significant difference between these 2 numbers. However, if you repeat this in high dimensions, you will find out that the distance between all pairs of vertices is the same. And the reason for that is fairly simple. If you want to calculate the distance between 2 random points, x and y, what you do is you take each coordinate, take the difference of the coordinates, square it, and sum it up. Well, if x and y are random, the coordinates are random, x minus y squared is a random number, you're adding up a large number of random numbers, and the law of large numbers says it'll be very close to the expected value. Okay. What would happen if you looked at a cube in higher dimension? Okay, and let's make it a unit cube. So the volume of that cube, even if it's in dimension 100, is going to be 1. Okay. But what would happen if I took a unit radius sphere and I let the dimension go up? Well, what I thought is well, the volume will converge to some number. Maybe it'll be around 5 or something. No. The volume goes to 0. So if you draw a unit radius sphere in high dimensions, it has no volume. Okay, it's quite easy to just do the integration. But let me show you a consequence of that. Suppose I have a Gaussian probability distribution. And in just 1 dimension, almost the maximum of the probability distribution is at 0, and almost all of the probability is close to 0. It's within 3 standard deviations of 0. What if I did this for a Gaussian in high dimension? So in every dimension it's Gaussian dropping off. Well, again, the maximum of the probability density is going to be at the origin. But if I ask you, what is the probability density? How much probability is there within a unit sphere centered at the origin? Well, you'd integrate over the sphere, but since the sphere has 0 volume, the answer is 0. There's no probability density near the origin. Okay? In fact, it's all in a little ring, which is out at the distance square root d from the origin. And this ring, if it's a unit variant Gaussian, is about 3 units wide. The reason there's nothing farther out is the Gaussian is dropping off exponentially fast, and as the sphere grows, it's only growing as n to the d, where d is your dimension. So it's all in this narrow ring. Well, suppose I have 2 Gaussians that are generating data, and I have one of the data points, and I want to know which Gaussian generated it. I should easily be able to determine, even if the Gaussian centers are close together, because these 2 rings essentially don't overlap. Okay? So just to do an experiment, I generated, I think, 1,000 points from each of 2 Gaussians. And if I asked you which Gaussian generated which point, only I didn't show you the colors, I showed you that, you might say, how am I going to do it? Well, it turns out there's a simple algorithm that will separate them. And I'll show you the algorithm. What I'm going to do is I'm going to take that annulus and I'm going to approximate it by a sphere of radius square root d. And the average distance between 2 points on a sphere, if you generate random points on a sphere, they will be distance square root 2d apart. The reason I know that is the following. I generate the first point. And then what I'll do is I'll change my coordinate system to put the point up at the North Pole. I'll generate the second point. And I know that that second point is going to land on the equator, or very close to it. How do I know that? Because it turns out that the surface area of a sphere in high dimensions is all concentrated at the equator. So these 2 points and the origin form a right triangle. The sides are square root d, and the hypotenuse is square root 2d. So if you generate points in high dimensions, they will be that distance apart. If they're from 2 different Gaussians, then, and if the Gaussian centers are distance delta apart, they'll be square root of delta squared plus 2d apart. And just in the interest of time, because I want to talk about some other things, to be able to separate them, all I need is to make sure is the Gaussians are far enough apart so that square root of delta squared plus 2d is greater than the square root of 2d plus some gamma. That gamma came because I made some approximations. Okay? And what that says is that as long as they are apart by an amount which is the 4th root of the dimension of the space, you can separate them. You can actually do much better than that, and I'll show you in just a second. One of the things you're going to want to do is dimension reduction. If you have something in high dimension, what you'd like to do is project it all down to a lower dimension. And it turns out that that's going to be pretty good because there's a theorem that says all pairwise distances will, the ordering of them will be preserved. So what I'm going to do is project the points onto the space containing the centers of the Gaussians. And you're going to ask me, how did you find the space containing the centers of the Gaussians? And I'll mention that in a minute. But I can reduce then the dimension from d, we start it down to k, which is the number of Gaussians that you're dealing with. And what's interesting about this is notice that when I project these points down, the centers stay the same distance apart because they're on the space that I'm projecting onto. But notice that all of the distance off of that line is Gaussian noise. And what I'm doing when I'm projecting down is I'm getting rid of noise and not losing any signal, so I have a better chance of separating them. And if you do this, you can separate them even if they're much closer together than what the previous slide suggested. It's just, this has to be greater than some constant involving the number of Gaussians and the error term. That's all. Okay, so what you've just seen is you've seen a science space for high dimensions might look like. what other areas do we need a science base for? And I picked high dimensions to show you because people have kind of worked on that. They understand it, and there's a lot of theorems and so forth. But there's a whole host of areas which are just ripe for working on. One of the things, ranking. We rank literally everything, restaurants, movies, books, web pages. Faculty rank students, students rank faculty. By the way, it turns out that the ranking is a multi-billion-dollar industry. And there are two parts to it. There are people that run search engines that want to rank things accurately. And there are people who own companies who want their company to appear at the top of the ranking and are willing to pay a fair amount of money to get that. And so the search engines then want to come up with ways to rank which can't be manipulated, or at least if they are manipulated, they will know it so that they can put a flag or something. One of the things you should know there is that if you have individual rankings and you want to combine them, there's no way to do that if there are three axioms that if you agree that you want to preserve, then an economist by the name of Arrow showed that you can't do it. And basically what he showed is that there's no fair way to vote. But you should at least be aware of that literature. Collaborative filtering. When you buy a product on Amazon, they give you some other products that you might like to buy. And usually they're fairly accurate. How did they do that? How, based on one purchase, can they figure out what you want? Well, there's a whole theory of collaborative filtering which helps to answer questions of that type. Dimension reduction, I talked a little bit about that. Extracting information from large data sources. This is going to be something which is just very important. Probably one of the most important areas. There are going to be noisy data structures, but they're going to be enormously large. They're going to have missing data. And one of the things you might want to do in collaborative filtering can help you with filling in missing data. For example, biologists want to find proteins that interact. They want to find clusters. So they make a graph where every vertex is a protein, and they put an edge between two proteins if they interact. However, it costs them money to put that edge in because it requires a laboratory experiment. And so the databases that you get from biologists are missing many of the edges. And what you would like to do is you'd like to run a program which says which edges should be, with high probability, should be in, because then the biologist can go and do the laboratory experiments for those without doing things which obviously are not going to go in. Social networks. Just enormous number of problems here. But what I want to do is I want to just summarize in hoping I got across the following points. This is really an exciting time for people in computer science or information science. And there's just a wealth of data out there. And it's important to develop the science base to support these activities. And most of it, what you're going to be doing is you're going to be squeezing out 0.5% of performance or something like that. And that may say that's a trivial amount. But when you look at the scale of these things, 0.5% usually translates into $10 billion. So these are really important things to be working on. And what I want to do is I just want you to remember that institutions, nations, and individuals who position themselves for the future will benefit enormously. And I just want to thank you for giving me the opportunity to talk to you, and I'll be happy to answer any questions that you might have.
I'll go ahead and ask the first question.
Yes.
For our daily living,
Yeah.
we just need a few things. People are, of course, buying more and more things, but they're just sitting somewhere in the closet. So one of the most important things, and I'm just increasing your application by one, one of the most important applications for a person is to find a spouse.
Right.
And there are billions of possible is possible, right? So one of your application could give an answer to that one, that would be great.
Yeah, that's one I'm not that, I'm not sure how well the social sites for finding spouses work, although I do know a few people who have used them and have found their spouses that way and seem to do well. This one. By the way, I didn't mean to suggest at all that the list of things I put up here was anything. All I did is there are thousands of applications, and I just picked one from each, just to try to get across to you just how complex and how many different interesting and exciting problems there were. Yes?
So you've talked about mostly theoretical future. What about the system side to support these kind of things? I mean, if you have exabytes of data, you would also need something to support exabytes of data. So what do you think would be future of computer science, let's say, in the side of systems?
Yeah, no, I think, see, I don't know that much about systems because I'm not there, but it's going to also be an incredibly big area because many of the systems don't work that well, and how you're going to get things which the average user can use. I mean, just things, when I came here, I had problems with airline flights because they were, why the computer, since they knew where I was going and knew things in planes, why didn't they get a hold of me and say, you're not going to make it today unless you go a couple hours earlier and take this flight in a different routing and so forth. And if I'm on a plane and it's going to arrive late and I'm going to miss my connection, why am I not rebooked already on the, on the next flight, and I just pull out my cell phone when we land. And there's just thousands of things like this. And how we're going to store data and how we're going to be able to access things. I mean, there's 845 million photos out there. You think, how is anyone ever going to look at them? And there's just enormous numbers of systems, and architecting them. And also, there's a large number of our systems, like our electrical network and things like this, which depend very heavily on computer systems, and are they reliable, and how can they help? So I think that area is going to be tremendously important. It's just I'm not the person to really ask about the problems. Yes?
Are we teaching the right math for these new problems?
Well, one thing I understand here, you've added probability and statistics, and that's great. And I think that's probably the biggest change, that probability and statistics. It used to be discrete math was very important, but I think it's going to be replaced by probability and statistics. Now, you say, why am I saying replaced? And that's because you can't keep adding courses. You have to do a substitution. And, but it's, I can tell you, though, about a mismatch in this country. If you talk to Microsoft, Google, Amazon, and people like this, they say they are trying to hire something like 70,000 people. There's 70,000 jobs that they can't fill. Yet we have an 8% unemployment problem. And what that says is our educational system, there's a mismatch between the skills we're developing and the needs of the country. And it's not the fault of the computer science department. I mean, they're doing a very good job. Somehow the message that society is sending, people are going into other majors, where they're not going into the majors where they get the math and the physics and the computer science that's needed. And I'll tell you, since I consult for Microsoft, and I'm involved in, they're going to China to set up a facility to hire 5,000 people, and we're negotiating over a location for it. Those could be 5,000 American jobs, but Americans don't exist. So you ought to tell your president here that he ought to realize that information is one. And by the way, I didn't say anything about biology, but biology is going to be another enormously important. So don't, I'm not saying this is the only one, but your department, the department here, I think has 45 faculty. That's nowhere near the size that is going to be needed. They ought to be thinking of a college with a number of departments, and they ought to be thinking, where in the university should it be located when they build buildings in the future? And because they're going to interact with economists, with sociologists, so they want to be somewhere in the center of campus. And those institutions, who position themselves are going to benefit. Yes.
So this is more towards your many years in the field, and it's a broad question. What would you say has happened to the industry research, university industry relationship over the last, not keeping out the government, just to keep it concrete?
Right. You should understand why industry has research labs, because it's a little bit different than what many people think. Industry is faced with the following problem. They either have to be proprietary or they have to be open. Okay? If they're proprietary, they're not going to compete with this enormous science establishment in the world. So that's a loss. If they're open, then their competing companies are going to benefit from their science as much as they are. And it is for that reason that our country decides to fund science. That's why the National Science Foundation funds science, because the funding for science would not be at the right level if you left it up to the free market for those reasons. So what companies do is they make the following investment. They say, we're not going to actually drive basic science. But what we want to do is we want to have enough world-class scientists who are going to international conferences around the world that they're aware of what the science development is in areas that are important to them. So that if there was a breakthrough somewhere in the world that could upset their business or could do something, they would be able to bring it back to this country, reproduce it, develop it, and so forth. So that's one of the reasons. The other reason why they give small amounts of money to universities is they want to hire your undergraduates and they want to have a relationship with faculty so that you will, when you have someone good, you'll tell them and so forth. So that's kind of the way science works. And there hasn't been a change. I mean, the only change is AT&T was special. Because they were a monopoly, and the way their profit, they got a 10% profit or something, and research was part of their cost. So the more money they spent on research, the more money they made. So that was kind of a unique situation, and when we deregulated the telephone system, that disappeared. But it was AT&T that invented the transistor and things like that, and it had tremendous impact there. Yes?
To what extent, I mean, you talk about needing to deal with these larger and larger data sets, but are we really getting more out of the large data than a sample of the small data? What are the problems where you really have to look at all that large data?
Yeah.
And you're going to learn something different than you might learn on a small sample.
Yeah, no, that's a very good question. Because if you sampled well, you ought to have a good reflection of the composite data. And I don't know exactly how to answer that. I think, examining, I don't know if examining parts of it, you may figure out how to, in examining parts of it, to find different trends or different unusual situations, things like that. It may be that we don't have to look at it all. And there are a lot of advances in learning theory, which suggests for certain kinds of things that that's true. Yeah.
Well, let's thank John.